So, Assalamualaikum warahmatullahi ta'ala wabarakatuh. So, this is the second part of our video. So, models of traffic flow. With the basic relationship among traffic flow, speed, and density formalized, attention can now be directed toward a more microscopic view of traffic flow. That is, instead of simply modeling the number of vehicles passing a specified point on a highway in some time interval, there is considerable analytic value in modeling the time between the arrivals of successive vehicles. So the most simplistic approach to vehicle arrival modeling is to assume that all vehicles are equally or uniformly spaced. This results in what is termed or deterministic uniformal arrival pattern, under the assumption in that the traffic flow is 360 vehicles over h. So the number of vehicles arriving in any 5 minutes time in interval is 30, and the headway between all vehicles is 10 seconds, because h will equal to 3,600 over q. So, however, actual observations show that such an uniformity of traffic flow is not always realistic, because some 5-minute intervals are likely to have more or less traffic flow that other 5-minute interval. Thus, a representation of vehicle arrival that goes beyond the deterministic uniform assumption is often warranted. So, Poisson model that account for the non-uniformity of flow are derived by assuming that the pattern of vehicles arrival at a specified point corresponds to some random process. The problem then becomes one of selecting probability distribution that is a reasonable representation of observed traffic arrival pattern. An example such as distribution is the Poisson distribution. 8. So, example. So, an observer counts 360 vehicles over h at a specific highway location, assuming that the arrival of vehicles at this highway location is Poisson distributed. So, estimate the probabilities of having 0, 1, 2, 3, 4, and 5 or more vehicles arriving over a 20 seconds time interval. So, this is the solution. So, the arrival rate is 360 vehicles over h, or 0.1 vehicles per second. Using this in equation 5.23 with t is equals to 20 seconds, the probability of having exactly 0, 1, 2, 3, 4, and 5, 1, 2, 3, 4, and vehicles arrive are. So, the solution is P of 0 equals to 0.1 times 20 of 0 squared. E is E squared, I squared of 0 negative 0.1 times 20 over 0 punctuation is equals to 0.135. So, same process lang hanggang sa P of 4. Then, for 5 or more vehicles, P of n less than or equal to 5 is equals to 1 minus P of n greater than 5. So, equals to 1 minus 0.135 minus 0.271 minus 0.271 minus 0.180 minus 0.90 is equals to 0.053. Is the histogram of this probability shown in 5.5. So, this is the histogram. So, next example is the traffic data are collected in 60 seconds intervals at a specific highway location as shown in table 5.1, assuming that traffic arrivals are Poisson distributed and continue at the same rate as that observed in 15 time period shown. What is the probability that 6 or more vehicles will arrive in each of the next 360 second time intervals? So, 12:15 p.m. to 12:16 p.m., 12:16 p.m. to 12:17 p.m., and 12:17 p.m. to 12:18 p.m. So, ito yung solution. Same lang rin doon sa kanina. So, the summation of this probability is the probability that 0 to 5 vehicles will arrive in any given 60-second time interval, which is, so this is the solution. So, 1 minus P of n is greater than or equal to 5 is the probability that 6 or more vehicles will arrive in any 60 seconds time interval, which is, so this is the table 5.1. Meron siyang, sa table, makikita nyo yung time period niya and the observed number of vehicles. Next is the assumption of Poisson vehicles arrival also implies a distribution of the time intervals between the arrival of successive vehicle time headway. To show this, note that the average arrival rate is, so ito na. So yung average vehicles rate in vehicles per second, and the Q is flow in vehicles over H, and the 3,600 number of seconds per hour. So, chapter 5. Fundamental of the traffic law, and so substituting equation 5.24 into equation 5.23 gives P of n is equals to QT all over 3,600 squared of n E squared of negative QT all over 3,600 over n punctuation. So, note that the probability of having no vehicles arrive in a time interval of length t, P of 0 is equivalent to the probability of a vehicle headway being greater than or equal to the time interval t. So, from equation 5.20, so example 5.6. So, consider the traffic situation in example 5.4, 360 vehicles over H. Again, assume the vehicle arrives are Poisson distributed. What is the probability that the gap between successive vehicle will less than 8 seconds? And what is the probability the gap between successive vehicles will be between 8 and 10 seconds? So, this is the solution. So, by the definition, P of H is greater than T is equals 1 minus P of H is less than or equal to 1. This expression gives the probability that the gap will be less than 8 seconds as P of H is greater than 8 is equals 1 minus E squared of negative 360 times 8 over 3,600 is equals to 1 minus 0.449 is equals to 0.551. So, to determine the probability that the gap will be between 8 and 10 seconds, compute the probability that the gap will be greater than or equal to 10 seconds. So, P of H is greater than 8 equals 1 minus E squared of negative 360 times 10 over 3,600 is equals to 0.368. So, the probability that the gap will be between 8 and 10 seconds is 0.081. Then, the next is, makikita nyo dito yung graph. Next is the limitation of Poisson model. So, empirical observation have shown that the assumption of Poisson distributed traffic arrivals is most realistic in lightly congested traffic condition. As a traffic flow become heavily congested or when traffic signal cause cyclical traffic stream distributants, other distribution of traffic flow become more appropriate. So the primary limitation of the Poisson model of vehicles arrival is the constraint imposed by the Poisson distribution that the mean of period observation equals the variance. So for the example, the mean of period observed traffic in example 5.5 is 6.733 and the corresponding variance is 7.210. Because these two values are close, the Poisson model was appropriate for this example. If the variance is significantly greater than the mean, the data are said to be over-dispersed. So, and if the variance is significantly less than the mean, the data are said to be under-dispersed. In either case, the Poisson distribution is no longer appropriate and another distribution should be. Such distribution are discussed in detail in more specialized sources. So, queuing theory and traffic flow analysis. So, the formation of traffic queues during congested period is a source of considerable time delay and result in a loss of highway performance. Under extreme condition, queuing delay can account for 90% or more motorists' total trip travel time. Given this, it is essential in traffic analysis that one develop a clear understanding of the characteristic of queue formation and dissipation along with mathematical formulation that can predict queuing related elements. As is well known, the problem of queuing is not unique to traffic analysis. Many non-transportation fields such as design and operation of individual plants, retail, store, service-oriented industry, and computer network must also give serious consideration to the problem of queuing. So, next is the impact that queues have on performance and productivity in manufacturing, retailing, and other fields has led to numerous theories of queuing behavior. The process by which queues So next is the dimension of queuing model.